Okie dokie. So I think, if I remember correctly, we had just kind of gone through Sn1 and looked at the overarching ideas, I guess, right? The important things that we have to pay attention to. Right? So, what's the setup for an Sn1 reaction? What do we need to have around? Yep.
A weak nucleophile.
Okay, looking for a weak nucleophile. What else?
Good leaving group.
Hmm?
A good leaving group.
Okay, good leaving group. What else? Someone besides, so please, man, give someone else a chance.
Before it generates a carbocation, it prefers a tertiary leaving group.
Broaden that statement. You're not wrong, but broaden that statement.
It is quickest to react with a tertiary leaving group
Why?
because the carbocation will form more easily.
So the more stable a carbocation we could form, right, the more likely an Sn1 would be to happen, right? You guys with me on that one? You guys catch the subtle difference there, but important difference? Right? It's important to recognize, like Freddie was saying, that the rate determining step is the formation of the cation. So anytime we can make the cation formation faster, then it's going to make that reaction go faster, right? But just because we deal with tertiary cations all the time doesn't mean necessarily that they're most stable, right? Okay. You guys with me on this? Can you guys think of a cation that's more stable than a tertiary carbocation? I'm kind of lying to you guys, as I tend to do, right? You guys aren't going to do that. What could be a more stable cation than tertiary? Dr. H. There's nothing more stable than a tertiary carbocation. You're such a liar. Okay.
One that doesn't leave with a positive charge at all.
Oh, well then we have something completely different, right? Carbocations are by definition a cation, right? So they have to have a positive charge. Okay, so we'll hang on to that thought for just a second. So we need a crappy nucleophile, a pretty good leaving group. We need something that could stabilize the formed carbocation. What else? This one we haven't talked about too much, but we did mention it way back when, in the day, when life was easy, and all we had to deal with were elimination reactions. So the elimination reactions tend to be favored under high heat, right? Under higher temperatures, we tend to favor eliminations. Why?
They're related to enthalpy.
Related to, not enthalpy, but entropy, right? They tend to make more molecules than they start out with, right? And remember when we were looking at our Gibbs free energy, temperature and entropy are linked together, right? Delta G equals delta H minus T delta S, right? So as we increase temperature, we increase our entropic contribution. And if we get to a sufficiently high enough temperature, then we will probably favor our elimination. So if higher temperature favors elimination, then lower temperature. It's great. I don't know why, but it's always funny, like when you become a teacher and you start to notice trends in the way that, you know, when you guys like talk over each other, then you're like, well, wait a minute, I don't want to say something dumb while someone else is saying something. You guys both come to realization at the same time. Right? But yeah, as you guys said there, right? The lower the temperature, right, we probably favor substitution a little bit more. But there's a problem with that statement too, right? Say, damn it, of course there is. There always has to be some stupid exception. Or have we been heating up the reactions in the lab? Yes. How many of them? All of them. Why? Were we doing eliminations? Were we doing eliminations? No. So why were we heating them up then? Well, all reactions require energy to go, right? We call that activation energy. So as you add energy into any system, all reactions are going to proceed at a faster rate, right? All reactions will proceed at a faster rate. So it's kind of a lie to say that temperature, drastically favors elimination. It doesn't. It'll favor it a little bit, right? It'll favor it a little bit. But temperature also will make substitution reactions go faster, okay? So it's kind of what's the word I'm looking for? Maybe not contrivance. I've been using that too much. A thing. It's a thing. That's what I want to tell. It's a thing that we have to deal with. No, the point being that, remember, temperature increases the rate of all reactions. Okay? It's just that we, in this class, for a purpose, while doing chemistry on paper, let's say it that way, right? While we do chemistry on paper, we say that increased temperature tends to favor eliminations. And that's not necessarily an incorrect statement. Okay? So, there's other factors that we have to deal with. And that's a little bit of what we'll talk about today. All right. So, now that we have kind of our understanding there of all the different mechanisms, SN1, SN2, E1, and E2, right? Now, the tricky part becomes making sure that we can pick the right mechanism given the right conditions is what it is, okay? Now, a couple other factors that we have to deal with are things like solvent, okay? So we have two different types of solvents that we broadly deal with, mostly in the context of this series of chapters, I should say. We have polar protic. And we'll have polar aprotic. Okay? So polar protic and we have polar aprotic solvents. I'm using the book again. What does the book say?
I don't know.
Oh, you didn't read it. Oh, you just have it there for the show. Oh my goodness. All right, good. Don't read it. I might be wrong on everything. So. I don't know this stuff. So what do we mean by this? Okay, well, what does it mean to be polar?
Not have a balance of charges in the molecule, like one end might be negative or partially negative, one end might be partially positive.
Right, we've got a permanent separation of a permanent separation of partial charges, right? Permanent separation of partial charges. Permanent separation of temporary charges. That's the way it works. A permanent separation of partial charges, right? Well, I've got one end that's feeling slightly more negative than the other, right? What's that usually based off of? Electronegativity, right? So if you've got like a carbonyl group, right, your oxygen in your carbonyl group is going to be feeling more negative than the carbon that's involved in the carbonyl group, right? Okay, so that's what the polar means. What does it mean to be protic?
Protons.
Yeah. Okay. They're like everything in organic chemistry has protons. Well, remember, when we say proton, what do we really mean in this case? Hydrogens that are acidic, okay? So we're looking at potentially, let me think of a better term here. We're thinking of hydrogens that can act like acids under reasonable conditions, right? What I mean is, technically speaking, every hydrogen could be acidic, right? You just have to put it at, harsh enough conditions and that'll happen. But right, we're looking at things that can act like an acid under reasonable conditions. For instance, can water act like an acid? Sure, right? Can an alcohol act like an acid?
No, it's not.
Sure, right? In fact, we said that alcohols are amphoteric, right? They can act like acids or bases. And so those are our examples of polar protic solvents. Waters, alcohols, okay? If you have some amines around, they might consider that protic too, okay? Okay, so what's it mean to be aprotic then? Well, prefix A means without, right? So what does it mean to be aprotic? Doesn't have acidic, right? Hydrogens on it. So, as with most things in life, right, we should always ask the question, what's the same and what's different? Well, both of these solvent classes are polar, which means they both have negative and positive ends. Right? What does that tell you? So one of these solvents is going to favor an Sn1, and one of these is going to favor an Sn2. Okay? So it can't really deal with the polarity, right? The polarity is the same in both of these cases. So it's got to deal with those acidic hydrogens, right? Let's think here for a second. Oops. Here's an example that we've probably never seen before or discussed, okay? You notice how we just keep adding more and more information to the exact same reactions, right? You see why this chapter tends to be, let's say, confusing, or at least challenging, because there's so frickin' much that we have to talk about, right? Man, it sucks to be undergrads. Oof. Feel sorry for you guys. Next exam. Right. But anyway, right? What do we have here? Okay. Got an alkyl group. Got a good leaving group. Primary. Got a strong base. A good nucleophile, right? An unhindered base. An unhindered nucleophile, right? Remember what we talked about last time? Our buddy T-butoxide and LDA, right? Thank you, one person remembers. Cole, I appreciate it. What happened to the rest of you guys? Sorry, Dr. H, Miami clubs, they were calling all weekend. Right? So we've got an unhindered base and unhindered nucleophile. What's this? How's this behaving in our reaction? Therefore. It's a conjugate acid of our base, right? That's important. That helps kind of establish an equilibrium for things. What is that? Let's see.
It's a solvent.
It's our solvent also, right? The way you set up this reaction is you take your alkyl halide, you dissolve it in some ethanol, right? Well, in general, right? You dissolve in some ethanol and you might cut in some sodium or something like that. Okay, and then you end up generating the O with a minus charge there at the top. Okay? So the ethanol is our solvent. Got it? What kind of solvent is it? Does it have negative and positive ends? Yeah, so it's polar, good, okay. Does it have an acidic hydrogen? Yeah, so it's polar protic, okay. So there's an example of a polar protic solvent. Water is another example of this, right? What's going on with these solvents? Water, ethanols, amines. It's almost as if they have a special property we should always pay attention to.
They have oxygen.
Mm-hmm. You do.
Maybe oxygen secondary.
Primary. As soon as I say it, you guys are going, oh, of course.
Lone pairs.
Hmm?
Lone pairs.
They do have lone pairs. That is true also. What's bound to the oxygens?
Hydrogen.
Huh. What's the boiling point of water? Is that pretty high for such a small molecule? Interesting.
Oh, hydrogen bond.
Ah, hydrogen bonding. Got it? Alcohols can hydrogen bond. Water can hydrogen bond. Amines can hydrogen bond. Okay? So I have these hydrogen bonding solvents. So guess what these hydrogen bonding solvents are going to do? They're probably going to hydrogen bond, right? You guys get what I'm saying with this? Have we ever thought about, like, what is the structure of, these species over here? So here's what I mean. Okay? So let me change colors here. So let's take a look at this. Okay? So here is, my gosh. Perfect. All right. There's my oxygen with the lone pairs and my negative charges, right? And it's full of glory. Behold. Well, this is in solution, right? So is this O with a minus charge that kind of floating out on its own, just hanging out? No, it's in what? A solvent. Is our solvent polar?
Yes.
Yes, so what does it mean to be a polar solvent? That it has negative and what? What type of charges? Positive charges, interesting. What charge does this have though?
Negative.
Negative. Huh, is there some concept that's important here? What happens with negative and positive things? They attract each other, right? They attract each other. Just like your negative grades attract positive responses from me, right? I'm just kidding. And I'm joking. You guys aren't laughing, oh no. Right? If you have something negative, they're going to attract things that are positive, right? So how is this arranged here? Well, we've got our hydrogens, okay? And what are they doing? Well, those hydrogens in blue are feeling pretty positive, aren't they? Yeah. Are they going to be attracted to something negative? Yeah. So what? Who cares? What impact would this have? So you got all these solvent molecules surrounding that negative. Let me ask you guys a question. So the reaction at the top, right? What's going to happen? What mechanism is going to be the major dominant mechanism? Sn2. How do you guys know? We've done this 50 times and you don't. How do you guys know? What's my evidence for an Sn2? Primary leaving group. Why is that important?
Because there's no steric.
You're just going to talk over her? How rude. Geez, will you apologize to the young lady for that? No, but you're right. So what were you going to say, Freddie?
There's just little steric hindrance.
Okay, what other evidence do we have?
Strong nucleophile.
So strong nucleophile, good. What else?
It's unlikely that a double bond will form on primary carbon.
What do you mean?
So if an elimination were to happen, you'd have to make a pi bond on primary carbon.
It would have to make a terminal alkene, right? Right? It could still happen, but it's not as preferred, right? That's what you're, yeah, okay, that's a good idea. It's the big picture with Sn2 reactions. What do we always have to pay attention to? The big defining thing. Give you guys nuggets of wisdom every day, okay? Not tasty nuggets like the chicken kind, but wisdom nuggets, like the useless kind. So if you remember, I said something, I think it was Friday, it might have been Wednesday, I forget now. But I said, if you're ever stuck, right? If you're ever stuck in any chemistry class, and you guys are all off at graduate school becoming chemists. Everyone always laughs at this. It's good. Look, have I ever told you guys like my personal story of becoming a chemist? No. So I started out in computer science, okay, and then I liked sunshine, and so I just so we kind of changed that. I went to biomedical engineering. And then I said, that's a lot of math, right? But actually what it was, and so I didn't start out as a chemist. And so I went through general chemistry, right? My freshman year, it was actually the first class of the day. I've always been a morning person, so whatever, 8 a.m. class is not a big deal for me, right? But I went through general chemistry, I'm like, what's the point? Like, oh, okay, you know, whatever. Right? Went through general chemistry too, and ugh. Right? I didn't like chemistry, right? I really didn't. It wasn't until I became, an organic chemist where I really started to enjoy it, right? So this stuff is what changed me over, right? And I say that because you guys don't know, right? I didn't like chemistry, and God said, watch this. Right? And they're all laughing up there, right? We know that God has a sense of humor, right? Because he said we're made in his image. So if we enjoy laughter, I believe he put that in us also, right? So I hope he's as sarcastic as I think he is. Yeah, you did a great job teaching, Patrick. All right, thanks, God. No, that's not it, right? Of course not. But anyway, right, the point being is whenever we're stuck, right? You guys are in graduate school, becoming chemists, and you're stuck. You don't know where to start to come up with an answer. Two smart things. We can always start our explanation at. What are they? Sterics and electronics, okay? So when we're dealing with an Sn2, what's kind of the big thing we have to pay attention to? Sterics. Got it? Okay. What's the mechanism for this Sn2 reaction that's going to happen up there at the top? Go ahead and draw it up. World's easiest mechanism, right? 2 arrows, no fuss, no stupid intermediates, right? No rearrangements, no shifts, none of that stuff. What attacks what?
The oxygen attacks the carbon.
Which oxygen?
The one with the negative charge.
Hmm?
The one with the negative charge.
The one with the negative charge, huh? How's that oxygen with the negative charge? What's its immediate environment? It's hydrogen bonding with all those other solvents. So when that oxygen with the negative charge moves to attack the carbon, what's it have to deal with? All those stupid solvents that are in the way, right? Are those solvents everywhere? Yes. Are they following wherever that negative is? Yes. So what does that add? If we surround our negative charge, what are we basically doing? We're adding more sterics, right? Because those solvents have to move out of the way before we can start to make the bond to that carbon. Got it? Because right now that stuff's tied up with all the hydrogen bonding. We have to push all that stuff out of the way. Do you ever get? Never mind. I've said enough dumb things today already. Okay. Don't worry, there'll be more. I promise. Does that make sense though? Right? If you're surrounding your nucleophile and it's hydrogen bonding the solvent, we've got to push all that stuff out of the way before we can take that lone pair and make a bond, right, to the carbon. So that's going to slow down an Sn2 reaction. Okay? Good? Now, this will slow it down, but is that still going to do an Sn2 reaction? Yes, right? Okay. Load. Did I click the wrong thing? Oh, yeah, I definitely did. Okay. So, let's see here now. Okay. So let's start wandering down the same pathway, the same set of questions, I guess.
Is it a weak nucleophile? Or
Hmm?
is it a bad nucleophile?
All right, we've got a weak nucleophile there. What else?
Is it
Tertiary leaving.
Tertiary leaving group. So as soon as we see a tertiary leaving group, what can we eliminate in terms of mechanisms? Sn2, right? So now we're only down to E1, E2, right? And Sn2, Sn1, E1, and E2, right? Okay, so we got weak nucleophile, pathetic base, right? Good leaving group, tertiary position, with a polar protic solvent, right? We don't specify temperature, so we assume it's room temperature or lower, right? So we're kind of pushing towards an Sn1, okay? right? What's the rate determining step for an SN1? Formation of the carbocation. What happens in the rate determining step? It does, okay? You guys following along where I'm pointing you guys with this? Listen, so remember what we're talking about in these factors that we're dealing with today is how do we speed up or slow down certain reactions. So what we have to do when we're looking at this is look at the rate determining step. You guys with me on this? So this solvent has to affect something in the rate determining step. Got it? Is the solvent around everywhere? Yes. So it's got to help speed something up in the rate determining step. Got it? What happens to the leaving group as it leaves and after it's left? What happens to it?
Gains a negative charge.
Aha, right? So remember, right, there's our step to form the carbon, and we quickly draw an arrow and we pat ourselves on the back and say, behold, right, I have made a carbocation, right? And it just, okay, there, nice, sounds good, okay? But this is the slow step. What is happening in this step? The transition state, okay, the transition state, that should be blue. I just want to draw attention to something that completely changed here, right? The transition state is what? The transition state of a reaction is where bonds are being broken and made, okay? So if you think about this, we just draw one arrow and we say, boom, that bond is gone, okay? But that's not what happens. So as we learned when we're dealing with this concept of IR spectroscopy, right? That bonds are vibrating around, right? They're bending, they're flexing, they're moving, they're rotating, okay? So they're basically playing the accordion, right? And if you add enough energy into this, eventually the accordion will pull itself completely apart. Will separate the carbon from the bromine. Is that an instantaneous step, or is there a lengthening of the bond with that? Well, the accordion is getting stretched out, right? As I stretch the accordion out, what happens? I start to make what? Partial negatives and partial positives. You guys with me on this? Because the bromine is pulling the electrons with it. It hasn't completely broken the bond yet, though, right? But do I start to make these partial negatives and positives? Absolutely. So, follow-up question, who cares? So what? This is my rate determining step, right? The solvent has to affect this in some way. You have to make it easier for this to happen.
Does it attack the other side of the partial positive as the
Does what attack it?
negative
What negative?
on the solvent?
Does the solvent do an Sn2 type reaction to attack the other side of this? Is that what you're asking?
Yeah,
Yeah. What do we think?
that as like the leaving group is leaving, then something else is going to be coming in.
You're on the right track. I'd be careful with what you're saying here, though, right? Because you're like, I think I'm going to try and do an Sn2. Can't really happen that way.
Does the incoming group push the bromine off?
That would be an Sn2 reaction, right? We have to generate the carbocation first, right? What type of solvent do we have here? Polar or protic. What's special about that hydrogen bound to the oxygen? It's acidic and it can do what?
Hydrogen bond.
Huh. How's that hydrogen bound to the oxygen feeling?
So the hydrogen goes off of the oxygen onto the bromine.
Is that what happens? Is that what I've showed you guys? No, right? Be careful. So this is what I mean. Let me pause you guys here for a second, okay? I don't want you guys to be creative. I want you guys to be dull and boring, okay? What I mean by that is, don't come up with stuff that we haven't done in class, okay? I don't really, I wish there was some way I could kind of, I wish I was a poet, so I could kind of, use my words to express idea in brain, right? But all I can do is grunt and point, like, right? I am showing you guys the fundamental steps. If you guys draw me something other than the fundamental steps, guess what you're doing? Being creative, okay? Now, when can you guys be creative? When you get your PhDs, okay? Just like when you guys can start to skip steps, then you can be creative. Now, if I ask you, I say, hey, something unusual happens here, okay? What do you think happens? Can you be creative then? No, right? You're still following the same steps, right? The steps all have to be the same, okay? I'm not going to ask you guys something that drastically changes the rules of chemistry. Why? Because you guys are just learning this stuff. So I'm asking you guys to apply the same ideas we've been talking about to the billions of reactions that are present, right? All the same ideas are working behind the scenes. As soon as you guys believe me with this, then this stuff's all going to become easier. And you guys are like, well, I already believe you. I do you? Right? So, back to the idea here then, okay? We have this hydrogen that's bound to the oxygen, that's protic, it's feeling partially positive, so it's going to be attracted to the partial negative, okay? So what's it going to start to form between the negatives and the positives? It's going to start to form what?
Bond.
Hydrogen bonds. Got it? Are hydrogen bonds a good thing? Yes. Do they release some energy when they form? Yes. Right?
So it like separates the bromine, like surrounds it with the positives.
And does what?
And like forms a
It helps to stabilize it though. You guys with me on this? Remember at the beginning when I first introduced, I said the leaving group leaves for no reason. It does, right? It just packs its bags and goes. If I can make that separation easier though, right? By surrounding it with booze, right? Ethanol, right? Right? Joking aside, you guys, does this make sense? If I can form hydrogen bonds to help stabilize these charges that are formed, then I'm going to make this pulling apart easier, okay? So as we go through this transition state, right? As we go through this transition state, we start to form these hydrogen bonds. Right? So much like, or almost exactly like what was happening with our Sn2 reaction, right? The positives are going to be attracted to the negative, and they're going to start to surround it. The more negative that bromine becomes, follow along with me here, okay? The more negative that bromine becomes, aka the more we can stretch the accordion out, the closer the bond becomes to breaking, the more negative the bromine becomes, the more we can hydrogen bond to it, right? The more negative means we can surround it with more of the hydrogens, yada, yada, yada. The more stabilized it becomes. Good? Does bromine necessarily want to be negative? It's okay with it, right? But remember, every time we put a negative charge on something, we better have a good explanation for how we can kind of spread that out. Got it? You guys with me on this? So, what is the idea between protic and aprotic solvents? It all comes down to what? Hydrogen bonding. Okay? Whether it adds sterics or whether it, stabilizes through electronics. Got it? So, a polar protic solvent has an effect on favoring Sn1 with their polar protic, and Sn2 for polar aprotic. Is it a massive, huge influence that drastically changes our percentages? No. Does it have an influence though? Yes. Okay. Concentration. So again, dealing with this idea of Sn1 versus Sn2. What do we mean by concentration then?
Concentration of like the solvent and the substrate.
The concentration of whatever's reacting, right? What's the M word we used? Molarity, right? That's our that's our measure of concentration. I am telling you that concentration will favor an Sn1 versus an Sn2. So my follow-up question is, how, or why, or in what way, right? But you guys already know the answer. Don't you? You read the book and made flashcards on it. No! Ah. You had your chance, Annie. It's all good. Let's think about this thing, right? What does it mean to increase concentration?
You add more solid to the solid.
I dissolve more things, right? How could I increase the concentration of students in this class? Give everyone Adderall. No, not that kind of concentration. What would happen if I add students into this classroom, right? We would slowly start to fill all the seats in, right? There'd be a higher concentration of students. Got it? So we fill all the seats and I add more students. What happens then? Well, you guys have to start sharing seats, right? Would that get uncomfortable? Yeah, would you guys start knocking into each other? Yeah. And you guys gonna start fighting? No, Dr. H, we're all Christians, right? Right? Do you guys get the point that I'm making? As we increase concentration, things start to knock into each other more, right? You're driving down I-75, you're saying, you know what, I've had enough of this semester, time to go home, okay? You're driving down I-75 at 2 in the morning. Good? Yeah, it's nice, right? Police aren't out, right? Now you drive down I-75, you hit Tampa at 4:45 on a Friday. Damn it, right? There's a bigger concentration of cars on the road. Do you have a higher risk of getting into an accident? Yeah. Do you have a higher risk of collisions? Yes. You guys get my analogies? So high concentration favors what?
Sn1.
Okay, why do we think Sn1? Oh, he called on me after I volunteered. I'm just gonna be quiet from now on. No. Why, so what's your line of thought?
So, I only think that because I know, if more things, since, Sn1 favors, I think it's the opposite.
Okay.
Because Sn2 favors, a primary leaving group, when there are more things involved, it's easier to collide with that primary spot.
You meant to say SN2, right?
I guess so.
You said SN1, but
I mean SN2.
Okay,
that's
yeah.
what I meant.
So give me your statement then one more time, then, please. So in SN2, it
One-
favors.
It favors a primary leaving group,
Okay.
so the, by favoring the primary leaving group, the SN2 has more of a chance of, bonding at that primary spot.
What does?
The, I guess not the solvent, but
The N part?
right.
What does the N stand for?
Substitution nucleophile.
The nucleophile. Okay? So let me polish Freddie's thought here for just a second, right? Do you guys catch what he's saying? What has to happen for an SN2 reaction? The nucleophile has to find the carbon of the leaving group, okay? So you're driving down I-75 and you rear end the guy in front of you during traffic, right? During at 4:45. That's how an accident happens. That's how a reaction happens. We call it collision theory, right? If you guys remember, way back in the day when life was easy, this was last year when you guys were in Gen Chem, so before the Rona, right? You guys remember that far back? Everyone was happy, the children were laughing. Right? You guys learned about something called collision theory, and collision theory says that for a reaction to happen, the two particles involved have to come together at the right speed, at the right time, at the right angle, with the right energy, and then a reaction can happen. So there's quite a few conditions that have to get met for a reaction to happen. They have to come together at the right speed, at the right time, at the right place, blah, 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 all that kind of stuff. How could you make that more likely to happen? Well, one thing you could do is what? Increase the concentration. Remember, chemistry is all a statistics game. I think I've made this analogy with you guys before, right? You guys have to take a statistics course for the most part, and you guys have to deal with something called large number theory, right? Large number theory basically says the more samples you take, the more it approaches the average, right? If you flip a coin 3 times, or excuse me, if you flip a coin 4 times, it's probably not going to be a 50-50, okay? But if you flip a coin 1,000,000 times, what's going to happen? It'll be 50-50, right? That's just what large number theory says. Do we deal with large numbers in chemistry? No, we deal with massive numbers. We call them a mole of things. What's a mole? Times 10 to the 23rd. Is that a big number? Yeah, so it's all statistics, right? We have to get the molecules together in the right place, at the right time, at the right... If I increase how many moles I have, then we increase the chance for the collision to happen. Got it? What does the 2 stand for in SN2? Bimolecular in the... Remember, what we're talking about is how we can influence the rate determining step. If I have to get 2 cars together at the right time for an accident to happen, if I put more cars on the road, we're going to have more accidents. Got it? Is it going to affect SN1? No, because how many molecules are involved with an SN1? 1. Can you have an accident with yourself? Well, maybe. You can't rear end yourself. That'd be impressive. Right? You could trip and fall. I guess that's a different type of accident, right? But I think you guys get the analogy I'm making here, right? I hit a parked car before. I mean, maybe that's gonna... Still involves 2 cars, not great, right? Okay. You guys get the point, though, right? Concentration, if you increase concentration, we're gonna start to favor SN2s. Higher chance of collisions, higher chance of reaction happening, that kind of stuff. Okay? Cool.
Dr. H,
Yep.
would that be the same with, E2 reactions?
It could, yeah. So higher concentration, right? We'll just say X. More SN2s. Okay. Now just, all comes down to this idea of what the 2 and the 1 stands for in the rate determining step. We have to get those 2 molecules together for them to actually do something. It's easy for us to draw this stuff on paper, right? Because we say, oh yeah, these molecules are just together, yep, they're gonna come in, we draw some arrows, right? In reality, right, these things are kind of floating around in a pretty big space, okay? So we have to get them at the right place at the right time. Cool, all right, we talked about temperature. Ooh. We talked about, whoa, what in the world is going on here? We talked about temperature. Whatever. We'll figure it out, I guess. Now we talked about temperature already, how it's basically the rising tide, right? As the saying goes, the rising tide raises all ships. Okay? So we're going to make all reactions go faster, although we do have a tendency to make eliminations go faster. But that's a big kind of stretch there, okay? If everything else is the same, and the only distinguishing characteristic you have is temperature, then sure, go for an elimination over a substitution, okay? Higher temperatures would favor eliminations. Well, that's way on down the line. Okay? Let's take a little bit of a turn here, kind of looking at the same idea of comparing reactions. But maybe instead of comparing, let's say, all 4 of them, let's see how we could affect individual rates. Here's what I mean. Let's say that I have this molecule and I put in that reagent, okay? And let's say that I play the stoichiometry game where I just have one equivalent, okay? I have just one equivalent of this, and I have one equivalent of that. Normally we just say we have as much as we need, right? Well, let's just say we have one equivalent of our base in there. You see the question that I'm asking now? I'm saying that one of those halogens is going to react faster than the other. Okay? They're both primary. They have the same base. It's unhindered. You don't specify anything about temperature. So what's going to happen? The iodine is going to react. Why?
Because it's the better leaving group.
Got it. Iodine's a better leaving group. So if you're a better leaving group, what's that going to do? Well, it's going to make you want to leave. Okay? And if you want to leave, that means you're more likely to leave. And if you're more likely to leave, that means you're more likely to react. If you're more likely to react, then you're more likely to react. Right? You guys got it? So the strength of the leaving group, if we're comparing relative strengths, the better the leaving group, the more likely it is to react. Got it? So what we'd say here, 1, 2, 3, 4, 5. Got it? So looking at the relative rate of the leaving groups, pretty darn important. So let's focus in a little bit here. Now I know you guys enjoy spice, variety, changes. No, we're good. Just give us one thing. Right? All the leaving groups we've been dealing with so far are halogens. And truth be told, they're extremely important for that purpose. We're going to see a lot of chemistry happen with our halogens. They're coming and going, they're substituting, they're eliminating, all these kind of things. But we have some other important leaving groups. Okay? Let's draw them out. Got that guy? You got that guy? We'll add a couple more as you go through here and there. Well, what makes a leaving group a good leaving group? Well, when a leaving group leaves, it usually takes what with it? A negative charge. So how do we make something a better leaving group? Stabilize a negative charge. Can these guys stabilize negative charges? Oh yeah. Right? Oh yeah. Specifically, right, we have an oxygen with a negative charge, and that oxygen with a negative charge has what? A lot of resonance. A lot. So we have resonance stabilized leaving groups. This is a tosylate. This is a triflate. Our buddy triflate not only does it have resonance structure, what else does it have with it? Carbon bound to some fluorines. Inductive effect, drawing away that negative charge, okay? Stabilizing that negative charge. Are these things powerful bases? No. Sure.
Yeah,
Okay, why?
because they're weak bases.
They're extremely weak bases, right? Why are they weak bases?
They can stabilize the charge.
The charge is delocalized.
Right? They've got a delocalized charge, right? Delocalized negative charge. Extremely weak bases. Garbage, they're pretty garbage nucleophiles too. Even though they have a negative charge. Okay? Remember, not every negative charge means it's a good nucleophile. So weak base comes from strong acid, right? These are extremely powerful acids. Triflic acid is I forget what the pKa is, but it's well into the negatives, right? I think it's like negative 17 or something like that. That's massive, okay? So they're very, very, very good acids. Powerful acids make weak bases. And weak bases make good leaving groups. You guys catch me on that one? What makes a base weak? Because we can delocalize the negative charge. What makes a leaving group good? Delocalization of the negative charge. Got it? Now, we'll see tosylate come up in chapter 10, I believe, is what it is. When you see a tosylate, you'll see an O, a T, and an S like that, OTS. Okay? Where this represents OS Toslate's gonna have a couple different, or basically, let's say 2 main functions for us. The first is that it's gonna be a good leaving group. And the second is we'll see it react with alcohols, okay? We'll see it react with alcohols, and we can treat it like a protecting group, and we'll talk about protecting groups more in the second semester, okay? For the moment, toslate's a powerful leaving group for us. Good? Cool. I think that's a good place to stop. We'll pick this up on Wednesday, and I should have your exams back for you guys then. Okay, so I'm sorry it's taken so long. It's just logistics with some issue, the COVID stuff on campus, right? Cool. I'll see you guys on Wednesday.